Well, hello, friends. Before we start, let me give a quick shout out to the Patreon supporters. You guys are really, really sweet for supporting me and Serenity financially, and you've ignited this weird little dream in me that maybe one day we could take this to a crazy level. But for now, we're just gonna keep hacking and fixing bugs. But thank you so much for your support, and of course to all of you who come here regularly and hang out while I hack. Thank you all. All right, so today we are going to work on a problem with signals. So specifically, when we abort a process because of an assertion failure, so I can do that with the crash program here, then it will exit because of the abort signal. But the thing is that I would like to get a backtrace when that happens, because if I crash in some like normal way, then I get this crash dump here saying like, oh, unrecoverable page fault, null dereference, blah, 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 blah. And we get the backtrace. But for aborted, on the abort signal, we don't get that. And that's very annoying because we use the abort signal for assertion failures. So, and of course, when you have an assertion failure, then you really, really would like to see the backtrace. So I'm gonna try to fix this. And I know that there are gonna be some problems, and I don't exactly know how to solve them, but we'll get there. So first up, let me show you the assert macro, just so you can see what that looks like. Assertions.h. I guess in user space at least, we're using, where are you? This one, which becomes this one, which if the expression evaluates to false, then we call this function here assertion failed, which just prints this out on the debug output and then calls abort. And that loops forever because otherwise the compiler was mad at me. And here's what abort does. So abort will just raise the SIG abort signal, and raise is a POSIX API for sending a signal to yourself. And then we assert that we don't get here because we shouldn't. Because sending the signal to ourselves should invoke the signal handler immediately. At least that's how I understood the specification. So you shouldn't be able to get here. But when we do raise, then yeah, here's how it works. So we just kill ourselves with that signal. And as you may know, kill in Unix isn't actually kill, it's more like send signal to process. Anyways, kill is a syscall. It goes to kill, and then that ends up in syskill here in the process class. And if we are sending it to ourselves, so if the target PID is the MPID, the member PID of this process, then we send the signals to ourselves, and then we block the current thread so that the scheduler will stop executing and switch to the signal handler if needed. I guess I just realized that maybe there should be a fix me here. Fix me. If we ignore this signal anyway, don't need to block here, right? But I'm not going to investigate that right now. So let me show you what happens when we get a SIG abort. So let's search for SIG abort, which was, of course, the thing that we raised here in abort. So when we receive a SIG abort in thread, wait, who calls this? Oh yeah, so this is where we compute the default signal action for a given signal. And the default signal action is basically what does the operating system do if you haven't set up a signal handler, then it will do the default signal action. And in the case of SIG abort, if you don't set up a handler, then the default action is to dump core. And I think that basically what we should do is that for any signal where the default action is to dump core, we should dump a backtrace to the debugger, at least. Because we're not going to make a core dump thing right now, because that's a bigger project. But let's make a backtrace. Okay, so let's find out who calls this. And that's, where are we? I think down here. Okay, so this is thread dispatch signal. So we get here, the scheduler calls this guy. I can show you with the magic of Control-Shift-U actually in QCreator, so you can see who's calling this. It's called from here by dispatch one pending signal, which is called from scheduler here when we iterate over all of the pending signals. So we are in dispatch signal, and we don't have a handler set up for this guy, so the handler virtual address is null. Then we look at the default signal action, and we get here dump core. So for dump core, we should do a dump backtrace, and then we can fall through. I think we just have to annotate the fall through here, because otherwise we get a compile warning. I really like this attribute, by the way. It's a neat addition to the language. Okay, so let's just build some stuff, and it seems like we have to build everything, but that's fast. Okay, so now we'll start by just dumping core and see what happens. So crash -a. I don't actually see any backtrace. So I guess we should let's add some debug output here. So let's just say like dump core. No, dumping backtrace for I don't know, dumping core. Okay, that'll be fine. For I will say process, because I think that will just pretty print the process name. Oops. And then we crash -a. Do we get that anywhere? Core. Dumping core for crash. Yeah, so there we are, right. But we don't actually get anything coming out, so that's not great. Of course, the problem is, and I already know what the problem is, so this is as far as I got in my mind, and from now on it's kind of uncharted. So the problem here is that dump backtrace, it's really just meant to like dump the backtrace of wherever we are in the kernel right now. It's not like dump the backtrace of a process or something like that. So this is more like a kernel utility function that dumps the current backtrace. But in this case, we want the backtrace for a process. So we're gonna have to do something a little bit different. I guess, actually I can show you how dump backtrace works. So it's really quite hackish, but it does work. So what we do is we create a variable here on the stack, and then we take the address of that stack variable and basically pass that into what am I trying to say? We're taking we're not putting a variable on the stack. Rather, we are grabbing the base pointer, the EBP register, and then using inline assembly here to extract the EBP, and then we're passing that to this function called dump backtrace impl. And the EBP is the frame pointer for when we entered this function here. So dump backtrace impl can then walk the stack frames starting at that base pointer. This is all extremely i386 specific stuff. So when we eventually want to do a port to some different architecture this is going to need some rethinking and some abstractification, but not today. So anyways, enough about that. So what we're going to do, I think maybe we can look at what we do in procfs. So I'll show you what we have in procfs. We do have this facility that allows us to, oh, something went wrong there. We have a facility that allows us to look at the backtrace or the stack of like an arbitrary process in the system. So like if we're interested in what the Windows server here is up to, for instance, we can cat proc7 stack, and then we get this nifty stack trace. And you can see here he has two threads. He has thread 0, that's his main thread, and also thread 1. And that's actually the thread that's computing the CPU usage number, so that we can show this little graph up here that's done on a separate thread, and that's this thread here. But yeah, so the logic for extracting this might be useful to us actually. So let's go and look at that. So in procfs, everything is implemented with these callback functions. So procfs $pid stack. This is the function that gets called when we want the stack file for a given PID. So let's see how this works. So we grab a process inspection handle for the process with the PID that we're interested in. And actually, I can show you, like, let me show you all the things. Well, this is kind of curious, I think. If we go to proc7 and we ls with, let's make it a little bigger. Oops, make it a little bigger and show inodes. If you look at the inodes here, you can see that they are following sort of a pattern. And it's just using a little trick here where we store the PID in the inode number. So the inode number is like, contains the PID and what kind of file it is and some stuff like that. And then whenever we are asking the proc file system to give us a file, then we can look at the inode number to figure out which PID we're interested in. So that's what we're getting here. We're like extracting the PID from the inode identifier. And then we are getting a process inspection handle for that. And process inspection handle is also kind of a nifty thing, actually. It's this mechanism that pauses a process until it disappears. So like, as long as we have this handle here, then this process will be in being inspected state, which means that it can't run. So it just allows us to like inspect it basically and like generate this little proc file, which is kind of nifty. Of course, at some point, we should really look over the denial of service potential with this mechanism and probably limit it so that like one user can't inspect another user's proc files or processes, because that might make it possible for him to like keep doing that and then disturb that other user. But anyway, not right now. Okay, so that's enough. That's enough of that. Let's look at this logic here. So we enter the process paging scope for the process that we want to look at. That just means that we are switching out the whatever page tables we're currently using to the page tables for that process, which allows us to like actually inspect the memory of the process we're inspecting. And then we iterate over the threads in that process. And we make this vector of recognized symbols, which are just an address and a ksim, that's the kernel symbol. And then we walk the stack of each thread, adding the return address to that list of recognized symbols. And then here we try to symbolicate. Okay, so I think this will make a good start for this. So let's see. let's do something like process dump backtrace. Or maybe process for each thread. Thread, and then we'll say like debug thread backtrace, and we'll say thread dump backtrace. Okay, and let me just check if it's possible to send a thread to them. No, it's not. Okay, so we're gonna have to add a log stream operator for that. I'm just kind of adding these as I go. Stream post thread value. Can maybe do like thread. We can do that in the pointer, and then which PID it is, and also which thread ID it is. It's a pretty helpful serialization of a thread, right? I mean, we don't serialize the entire thread. We just print out some helpful info about it. I think that would be useful. And then, of course, we should return the stream so that we can actually continue streaming. All right, so now we're going to need to implement ourselves a thread backtrace. So let's just do that. Dump backtrace. You know what? Let's do one better and do it this way. String backtrace, and it should be non-destructive, so we allow ourselves to be const. And then we can do like this instead. Okay. Now we just have to implement this guy. So string thread backtrace const, right? And let's just make sure that we have the right ID here, because then I was thinking like if we make this nicely, then we can actually use this in procfs. We don't have to have duplicate implementations. So let's see. Let's just see what we were doing here wrong. For each thread callback not ignored. Right. For each thread, return iteration decision continue. Okay. Now, so the thing to know here is that this thread that we are calling backtrace on, it might not be the currently executing thread. So we're gonna grab one of these handles here, I think. Because this handle is not going to hurt us. It will just be a temporary thing for the duration of this function. And what did I screw up? I forgot inline. Okay. Okay, and then we'll have a handle, which means that that thing won't run. And then we can probably just grab all this logic actually, and let's see. So we'll need to include ack string builder. Okay, and then we don't want to do for each thread here, so I'm just going to do, should we say it like that? No, let's not say it like that. We remove all the thread dots. We can't call PSS because it's non-const, but we could make ourselves a const getter. Okay. And and also long. And finally, return builder to string, because we were using a string builder here to construct the entire backtrace. All right, so that's kind of cool. Let's test it out. You build a little faster, please. Maybe. Okay, where did they go? Here they are. We can actually do this here right away because I think this would be pretty simple. Builder append thread backtrace. Right. Because if we did everything right, then it would just work. And let's see, do we need to do that? We can just get rid of that. We're going to need the process paging scope and backtrace down. Oh, we did have it. Okay, yeah, right. So we don't need that. Do need that. Okay, let's see how this works. Okay, well that didn't work. Assert not being expected. Oh, right, because we already have an inspection handle, and then I'm creating another one here. So that's not really going to work. Let me defer to the caller to already have one. So the easiest way to do that is to require the passing of a non-const reference, because that means that the caller has to actually come up with one of those. And he can't instantiate a temporary, so we'll do it like that, and then we'll say handle, and then backtrace process inspection handle. I guess we can forward declare that. So process inspection handle. And you didn't like that because oh, just some stupid punctuation shit. All right, well, no, wow, I ran some not good looking command there. Backtrace. Wait, what's wrong with you? Can't bind to a value of unrelated. It's an ohm pointer? Oh shit, right. Okay, so let's do it that way. Forgot to save this file. Backtrace. Okay, so here is where we are going to have to also create a process inspection handle, just for this little thing. So this will be not entirely beautiful, but it is what it is. Auto handle is process inspection handle from PID. Red.pid. Can we just create one? Handle process. Does this work? Handle is not captured. Well, I'm sorry. Let me capture you by reference. Okay. So, wow, getting a little small here. Let's make it a bit bigger, actually. So let's see how this works then. Crash-A. Not being inspected. Did I totally forget to remove them? Yep, I did. Handle, right. So in this case, we should really use our own process, so we don't need that business. We don't need to name the handle. No matching constructor for paging scope. You know, this is logically non-const, but I'm going to be lazy here and cheat a little bit and just do process is const cast process, because I don't want to deal with making everything const correct right this very moment. So we'll just do it that way. Okay. Can we finally try this thing? Okay, so we aborted, and we got the god dang backtrace. Very, very cool. It's looking a little bit curious. I think, oh, maybe that's because the kernel symbols were out of date, because I was editing the kernel and recompiling it, but I never copied the new symbols into the file system. So we'll just try that one more time just to see what it looks like with real symbols. Yeah, so this looks much better, right? So we're in kill, and then we're blocking, and then we're in the block helper, and we yield, and then the scheduler is supposed to switch, and then the next thing that happens is that we crash, so we dump core. So it's pretty cool. And let's see how those files look. We got the same good stuff in here as before. That's pretty neat. There is that extra new line here. I don't like that. So let's see. Should we care about that? Maybe we don't care about that so much. Because I guess it's that the debug helper that we're using in thread CPP. Backtrace, where are you? This debug helper will always add a new line, and then the backtrace is going to end with a new line. But I think it's not the end of the world. So maybe we should, I mean, I'm thinking we could share even more code here, because these are essentially doing the same thing, right? We could put these into a process.backtrace. So it'll be something. I mean, yeah, we want every thread in the process to give backtrace. Otherwise, it's going to be a bit stupid. But we should maybe also show which thread is being signaled. But we're always signaling the main thread. Okay, never mind. Let's just do process backtrace. Okay, and then we'll do this stuff right here. And string builder, return builder to string, return process backtrace handle to byte buffer. This can be kind of nice, actually. And then let's see. Now we just need to add this function here. So I'll just put it up here, up top. Inspection handle. Okay, and it can be const. And this looks kind of nice. Okay. And then in thread CPP, then we can just do debug process dot backtrace handle. Very cool. Okay, let's see if that works out the way that I was hoping. very cool, very cool. And let's try to kill a process that's not ourselves. So I have to cheat here a little bit and look at what's abort. Is it 6? Yeah, so let's sig abort someone else. Why am I LSing? BS. Okay, let's do the launcher guy here. So kill -611. Okay, so how did that turn out? Launcher dumping core here. Okay, very cool. I think that's really good. So let's see what we have here that we can commit. Time for, of course, patch review. So first up in procfs, we are just grabbing this whole logic here for creating the backtrace for the proc file system and copying that somewhere else. And then this function ends up being very simple. It's just process.backtrace basically. Here I added a fix me to look into later. And then we're adding process backtrace, which just iterates over all the threads in the process and builds up a string that just contains all the backtraces for all threads. It's pretty cool. Here's the declaration of that. And of course, note the non-const reference handle that we require here so that you don't call this without having a handle. All right. Then here in thread, when we want to do the dump core default signal action for signal handling, then before we fall through to terminating the process, we dump the backtrace on the debug output. And this looks a little goofy here, but Clang format does it that way, and I just do what Clang format wants right now. Okay, and then here is basically what we had in procfs before. Just copied it here verbatim. We generate a string containing the backtrace for this thread, which is very cool. Okay, and then here's just the prototype for that, and here we had to add a const overload for getting the TSS. And oh yeah, and a way to actually send a thread to the debug output. But did we end up using that? I think we didn't. We ended up not using that. Well, it doesn't matter. We'll still have it. So let's say kernel dump backtrace to debugger for default signal action dump core. This makes assertion failures generate the backtraces again. Sorry to everyone who suffered from lack of backtraces lately. We share this code with the implementation, with the proc fib stack implementation. You can now share code. You can now get the current backtrace for a thread by calling thread backtrace. Yeah. And all the backtraces for a process. Yeah, process backtrace. Yeah, that's pretty cool. Okay, so I think we're gonna commit there, and maybe see it one more time because it's kind of nifty. Crash -a. We are definitely doing that right. Okay, and then let's crash some other way. That's still fine. And then let's crash someone else. So let's crash. Let's abort someone else. Let's abort taskbar number 9. plop. And here's the taskbar backtrace. Okay, so everything is good. And I think that's gonna be it for today's video. So if you made it this far, then I thank you for watching and for hanging out with me while I continue to work on this. And I hope you saw something interesting, and I'll see you next time. Bye.